Hello, welcome to the Global Composite Express webinar series. My name is Wenping Yu, Director of the Composite Design Manufacturing Hub. This webinar series is to examine the history, current capabilities, and the future of composites, and for the purpose with the goal to sharing the vast knowledge of the composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We have launched the Composite Design Manufacturing Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design manufacturing. We provide a very powerful website called cdmhub.org for the composite community to come together to carry out this mission. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives that CDM Hub started as a service to the global composite community. This webinar series is made available and possible by the support of CDM Hub sponsors, including Dassault Systems, Cytec Solvay, and Anna Swift. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org. An email will send to you once the recorded video is available online. The presentation will last about 45 minutes, and we have about 10 minutes for questions and answers. All attendees are muted. Please submit your questions through the Q&A box. After the presentation, the moderator will read your questions for the speaker to answer. Next, let me ask Professor Byron Pepes to introduce our distinguished speaker today.
It gives me a great deal of pleasure to introduce to you Professor Wim vanpaepegem. He is a professor of mechanics of composite materials at Ghent University in the Department of Mechanics and Materials and Structures. He holds a PhD in civil engineering from Ghent University in 2002 with a doctoral thesis entitled The Development of Finite Element Implementation of a Damage Model for Fatigue of Fiber Reinforced Composites. And he has a master's degree from the same institution. His thesis there focused in very much on finite element methods. He is the author of 235 science citation papers, 12 chapters of books, 14 running PhD theses, and 30 completed doctoral dissertations. He's also involved in 16 national and European projects and 4 research grants. He reviews 10 scientific citation index journals, serves on the editorial board of the Journal of Composite Science and Technology, Composites Part B, Polymer Testing and Fatigue and Fracture of Engineering Materials and Structures. And he's a member of the Executive Committee of the European Society of Composite Materials. I'm delighted to present to you today Professor vanpaepegem.
Thank you very much for this introduction, and also thank you once more for inviting me for this webinar. It's really my pleasure. First of all, a warm welcome to all ladies and gentlemen that are watching this webinar. I will say good morning, good afternoon, or good evening to you. So I will guide you through this presentation about multi-scale modeling of composites. It's a personal impression, so I will present you some work that we are doing in our group. So it's certainly far from complete, but I will try to give you some insights in our philosophy and way of working in this field. So first of all, to give you a bit an idea where I am talking from to you. So I'm sitting here in my office in Belgium. This is a small country in Western Europe, and I'm affiliated with Ghent University here in Ghent, and the weather is nice for the moment. So just one slide to give you a bit an impression what we are doing and how this is linked to this presentation today. Like Professor Pipes said, our background is mainly mechanics. So we work on experimental mechanics, on NDT, non-destructive testing, to characterize damage and understand how damage mechanisms evolve. And then, of course, the topic of today, computational mechanics, and some more work on composite processing. I promised in my abstract for today that I would try to link those two, experimental and computational mechanics. And also here and there, I will address a few experimental challenges that are really sometimes crucial to get your input or your validation of your models. So we try to support an approach where we combine testing and modeling in a tight way together. So this was just a brief introduction, and now the outline of the webinar today. First of all, I guess most of you are at least a little bit familiar with composites, so I will give you a short introduction about the multi-scale nature of composites and also their damage phenomena. And then I would like to take you through the story from two different angles, starting once from micro scale and bottom up, and then from macro scale or even structural scale and down. And every time have a bit the same structure, introduce you through concepts, show some results, and then, as I said, a few experimental challenges that are linked to it. And then finally, maybe a bit provocative, I put a smiley here. Unidirectional is still simple, to show you a little bit if you move away from unidirectional composites that is like in short fiber and textile composites. Also geometry becomes more complex and can be an additional challenge if you want to model damage mechanisms. So first, to start, composites are multi-scale materials. We all know they are made from dry fiber reinforcements that are combined typically with polymers. That's at least the majority of the composite materials. And once it's cured or consolidated, it can look like this, a black plate, which is in this case carbon epoxy. And if you then zoom in, we can see either individual layers, unidirectional orientation in each of these layers, or we can have short fiber layers. And I also use the word layers because you see here that due to certain flow characteristics, you can have a core shell effect. And you see that the short fibers are not perfectly aligned and also have different orientations. And then a textile composite, where you can also see the different layers in the composite, in this case, a plain weave composite. So this is what we typically call a mesoscale. And then if you zoom in here, or for example, here in one bundle, you see the microscale with the individual fibers surrounded by polymer. So I will start once from here and once from there, and we will meet up here in my presentation. First, just still a few things more to give you a bit orders of magnitude. If we have such different layers in a composite, one ply is typically a few hundred micron or even less if it's prepreg. And if we zoom in, we indeed have these individual fibers, roughly 10 micron in average diameter, polymer around it. And then this interface will also come back in my presentation, sort of nanometer sized interface between the fiber and the polymer, which has to make sure that they adhere well together. And then about damage, this has also this multi-scale nature. Like some of you will know already, typically when you have transverse loading, in this case transverse tension, damage can start very early with disbonds in the fiber matrix interface. And by the way, a beautiful picture from Olivier from our department, where you see the dibonds that then coalesce together. And if you then zoom out, you start to see a ply crack. And when that ply crack meets the boundary with a differently oriented layer, you might get delaminations. Here from Ilya Koch's group, you see a picture here where at the crack tip, you see that the crack deflects and you get a delamination. It can also happen at free edges or at rivet holes or in adhesive joints, you can have these delaminations. And now I want to take you to two different routes, let's say. Here now we have the zoomed out picture of a failed composite. These are stitched electron microscopy images together. And here you see a lot of damage and also final fiber failure. So we can start from this scale and go up, or we are more interested in structural behavior and we can start from this scale and try to introduce the damage. And this is what I would like to take you to. We will start with this route, and then in the second part, we will start from this route. So first starting from micro scale and introducing you a few concepts before we go to the results. First of all, if we start quite simple, and what is our objective in micro scale modeling? We would like to start from the individual constituents, being the fiber and the polymer, and later also introduce the interface. Have, in this case, to start just with elastic properties, to have the elastic properties of the fiber and the polymer. And here you can already notice that carbon fiber is not isotropic in stiffness, and the transverse stiffness is much lower. And we would like to predict the properties of the composite, which is the assembly of the fiber and the polymer. And to do that, we don't want to simulate the whole composite. We want to simulate a unit cell and apply periodic boundary conditions so that we only simulate one building block, let's say. And because the boundaries are conformal or periodic, we can tile the whole structure and predict the overall response. That's the idea. Of course, you see that this, what is called a square packing, is a bit too simple for reality. So this is sometimes the start of the modeling, square packing. And if you want to debug your models, you can even have an alternative square packing just to see if they get the same results. But then you move on and have a random packing of fibers. Here you see again the periodic nature. So the fibers are assembled left and right. You can get a full fiber again. But more realistically, you generate a random packing, which looks like a real microstructure. And again, you apply the periodic boundary conditions. I have to cut a bit corners in this short webinar, so a bit simplified, state of the art in the microscale simulation is typically done for these representative volume elements. Most of the time for thermoset composites, you don't find that many simulations for thermoplastic composites. And if you apply this transverse loading, what we will typically see first is interface failure and also a high stress triaxiality in the matrix. And very important is also the stiffness contrast. So your fibers are like very stiff and hard inclusions, almost obstructions or obstacles in your polymer. So they create stress concentrations, and the relative stiffness difference between the fiber and the polymer is important. So here you see carbon, glass, and steel fiber. The stiffness mismatch with the polymer, which is typically a few gigapascal, can be very different. And mostly we simulate static monotonic loading conditions. So that's a bit our starting point. And now zooming in a bit on the ingredients. So we have a CAD model, for example, then we mesh it. We have a polymer matrix mesh, we have fibers modeled, and we have this interface. Typically, we explicitly model it, either with cohesive elements or cohesive behavior, to also have this interfacial debonding made possible. And we do need already quite some ingredients if you look to just a starting simulation. First of all, about geometry. We need to define a volume fraction, which is consistent with the experiment. We have to decide about the local packing of fibers and also interfiber distance. The closer the fibers together, the higher the stress concentrations will be. And we need these periodic boundary conditions. And here you see exemplified, here you have one instance of your representative volume element. Here is zoomed in the boundary of this representative volume element. And you see that it matches perfectly with the adjacent instances. So it's periodic. The fibers are typically assumed linear elastic because most of these simulations are done in transverse loading in this plane. And then the interface, that becomes a bit problematic. We need to define an interface strength in mode 1 and mode 2. We also need to define a fracture toughness for crack propagation in that interface. And if the interface has failed and you apply, for example, compressive loading, we also need to define a contact condition, possibly with a friction coefficient. And the same for the polymer, you have also a lot of options, elastoplastic, or you can go for rate or time-dependent behavior with viscoelastoplastic behavior. You can have different behavior in tension and compression. You can add a damage model for cracking. And like I will show you later also, we can also add thermal properties to do thermal simulations. And then there is another question, which I will also discuss in the experimental part. And what about the properties? Do we take the bulk properties measured at coupon level? And are they the same as these tiny volumes here in between the fibers? And the solver settings I will not discuss too much here. So mostly use an explicit solver because convergence is not that easy. And then some results. First of all, if you apply transverse tension, indeed you typically see debonding at an early stage. So this shows the damage of the interface. And also the maximum principal strain in the matrix is quite high. So you have indeed also a high stress concentration in the polymer. When we zoom in more, when these bonds start to coalesce together, you also see a large plastic deformation in the polymer. And these fibrils of polymer stretch a lot. And we try to validate not only on transverse strength, but we also try to validate on opening angles of debonding. For example, Hobby Brunken's famous pictures to see indeed these polymer fibrils that stretch. This seems like a lot of ductility, but this is not in contradiction with the brittle observation at structural scale or at coupon scale. You see here these plastic deformation. What is the opening here? It's only a few micron because the diameter of the fiber is roughly 10 micron. So at macroscopic scale, this is still very brittle. But we can confirm indeed from scanning electron microscope, here you see this was originally around the fiber and also this part here around this fiber. So you do see a lot of plasticity. It becomes a bit more tricky when you go to compressive behavior. Here you see transverse compression. And there again, we try to validate our simulations by looking at shear bands and shear band angles, and also at details from experimental observations. Here you see a sort of cusp behavior or a sort of opening, and we also see that in the simulations. But we observe here also another problem. If you look in the next slide, you see stress strain curve for compression and in-plane shear. And the red line is the experiment. And the black bottom line is the simulation with bulk epoxy properties. You see that we are quite far below the strength in shear and compression of the measured one. If we adapt that to the in situ properties, which are then higher because of an assumed size effect, you see that we come closer to the experimental one. I will come back to this also in the testing to show you some evidence of that. But still a few more things about this microscale simulation is also about volume fraction. We assume a certain volume fraction in the representative volume element, but that is not always the local one which is driving the damage in reality. This can be the case for a perfect aerospace prepreg composite where the fibers are very uniformly distributed. But here you see a glass polypropylene thermoplastic composite, which is typically used for automotive applications. And you see that the tape, the fiber distribution in the thermoplastic tape is not so uniform. And there, if we increase the loading from left to right in transverse tension, you see that the cracks typically develop in the highly packed regions where the local volume fraction is a lot higher than what you assumed maybe in your RV. And another thing is voids. Sometimes when we get industrially produced laminates with quite low consolidation pressure, you can also see voids in the laminate. And also these can sometimes be a start of cracks. And those you can also somehow include in your RV by assuming a certain void content. And of course, obviously, these will be often initiation side of damage and reduce also the transverse tensile strength. And the last thing to mention about thermomechanical analysis. This is something we are recently doing, is not only applying periodicity in mechanical loads, but also have a temperature included. And in this way, we can start to look at other effects like self-heating. So this is here the stress strain curve in transverse tension. You see at a strain rate of 100 per second. So this is extremely fast. This is more like for impact and crash simulations. This is the homogenized stress strain curve. And this is the temperature. You see that the temperature barely rises, but this is the homogenized temperature. If you look locally in your RV, you see a very high localization of the strain and a high increase, this is 50 degrees of the temperature. So here we have a model for the polymer that couples the plastic deformation to the heat dissipation, and the heat in turn will soften the material because this is a thermoplastic matrix and the glass transition temperature is close to 50 degrees in this case for polyamide 6, and you get a softening. So this is a self-sustaining effect. And then to conclude on this part, there are a lot of extensions possible. I retake my slide about the ingredients, and I added here, if you would move to fatigue or impact simulations, you come in quite some challenges. So what about the interface? How does it behave in fatigue, in impact? How strain rate dependent is it? How temperature dependent is it? You also need quite advanced models for your polymer. And you would also have to do progressive simulations in a finite element solver. So certainly not easy, and also certainly demanding or challenging for experimental side. This is where I want to still say a few words about the experimental challenges which are related to it. First, coming back to this bulk versus in situ properties. Here you see our attempt to shed some light on this. These are pure polymer fibers. So don't be mistaken, there's no fiber reinforcement, but to make the polymer in very thin volumes, we made fibers out of it. So here you see pure polymer fibers. You see the diameter here is very small. And when we test those in an electron microscope in a tensile stage, we see a lot of necking and very ductile behavior. When they are broken, so here you see 4 fracture surfaces, we also don't see any defects. And if we measure this diameter, we even have a correct measurement of the true strain at failure. And when we plot these ultimate tensile strains versus the diameter, because it's not possible to make a very controlled diameter, so you have here a scattering diameter. And here is the failure strain of the bulk epoxy, just a coupon scale. And you see, I admit there is a lot of scatter and we don't manage to make it smaller, but in average, the failure strain is much, much higher than the bulk. And also the strength is much higher. So we do see there some indication that maybe there is a size effect there. Another thing, this is really about the polymer, because on the micro scale, your polymer is an individual ingredient. This is about this thermomechanical behavior. So here you see pure polyamide 6, 50% relative humidity, relatively large strain rate. And the left is the longitudinal strain, and the right is with infrared camera, the surface temperature. We synchronize them, and we also map the temperature on the deformed shape. And then you see that indeed we have self-heating. So at this strain rate, the temperature rises quite a lot. And at a lower strain rate, 2 decades lower, the temperature stays just at ambient temperature. And then we also have strain rate dependent testing. You see here for that same polyamide 6, if you start from static loading up to very high strain rate, you see here this part is connected with this part, so it stretches really very long, and here it gets more and more brittle because of the strain rate effect. Why is this all important? If you calibrate your polymer model for the micro scale, you should not introduce any fictitious effects in the polymer that are physically not there. And that I want to illustrate with this last slide on the micro scale. So if you see here, we do, in this case, it's a compressive test on a pure polymer disk at very slow rate, at higher strain rate, and at very high strain rate. And this is the temperature which is plotted. And at slow strain rate, the temperature increase due to plastic deformation can just dissipate to the steel platens of your machine. But when you have a very fast loading, the temperature stays contained. And then you see that if you would approach your modeling with an isothermal model and you try to predict the experimental data, the experiments are in these symbols at different strain rates, you see that we overpredict the behavior a lot. While if we take this thermal coupling into account, we can see that at the higher strain rates, we get this softening behavior due to the temperature. And if you take that into account in a physically correct way, your model is also more accurate. That was a bit about the micro scale and all the ingredients and how to build these models and some points of attention. Now we move to the macro scale and come then way down again to the mesoscale and the ply scale. Again, first some concepts, then some results and some experimental challenges. When I want to start with you from macro scale, I thought we can just take large enough. So this is the LM glass fiber, LM wind power, blade, which is 107 meter. Siemens even recently announced a 115 meter blade. So these are about the largest blades for the moment. You see that little person standing over there. You also see here the adhesive joint to bond the two halves together. You also see the color of the core, the sandwich sections, and then of course the metal connection to the nacelle. These blades are tested in fatigue and also in static loading. Here you see a few pictures of certification tests where the blade is put under a certain angle. And then the blade is pulled downward with different cables to the ground. And this can happen in edgewise, flapwise bending, and coupled loading to also have torsion. And you measure the reaction forces and moments. You also have stroboscopic measurements of deflection, strain gauges, and so on. For quite some years already, we work on developing meshing tools to have an automated model generation for these large blades. So we can do that with pure shell elements. So this is a complete shell element mesh, except for the adhesive joint here. Or we can have a full solid mesh where the whole blade is meshed in solid elements. And these are then multi-layer elements describing the stacking sequence. And you see then in detail the adhesive joint and also the connections of the shear webs to the airfoils. All very nice, and we can do the same certification test that I just showed you before. So we have some winches that pull the blade to the ground, and we can simulate that behavior. But now back to our damage story. So here we have quite coarse meshing, let's say, compared to the damage mechanisms at micro scale and how to deal with them. So schematically, we have our ply cracks. I showed you the delaminations from the crack tips. We can have fiber failure and how to represent that. We could opt for an approach where you homogenize the material in between, like we did in the micro scale, but still keep the individual ply cracks modeled and even delaminations. I hope you understand with me that this is still computationally impossible. So we make these models on a smaller scale to validate our models, but we don't proceed in this direction. On the other hand, we went away the direction of more analytical models with the variational approach, where you try to solve the system where you do have ply cracks, you do have delaminations at the ply crack tips, and you might have fiber breakage for a certain layout, and you try to solve this system without finite elements. I will show you in the next slide how we do this, but if you can do that, then you could say I homogenize these plies with their damages inside, and the stiffness tensor becomes a function of crack density, delamination lengths, and fiber breakage volume. This is, of course, in the assumption that you stay with physics-based damage models and that you try to keep a link with physical representations of damage. Now, what about these models here? So some results to show you our philosophy in this approach. So Mohammad Haji Kazemi, one of our senior postdoc researchers, has worked a lot on this in the past years. And the setup is like this. You define a laminate where you have a certain array of ply cracks or even ply cracks with eliminations at the ply crack tips. And you have the typical loadings that you also are used to in classical laminate plate theory. So in-plane loadings, shear loadings, bending loadings, and we also added out-of-plane traction. And now we want to solve this without finite elements. You could argue, yeah, this is practically impossible. Well, it is indeed not easy. I mean, you get complicated equations, but to give you a hint how it works, you start with your solution from classical laminate plate theory, as if the material was undamaged. And then every crack is, put it a bit simplified, like a stress boundary condition. So we assume the crack faces are open, and then it means that on the crack faces, the normal and traction stresses are zero. And this is like a boundary condition, an additional boundary condition for your problem. If we do this for all of them and we properly separate the domains, you can solve this and have access not only to the global behavior, but also to the local behavior. So we also have the local stresses. And we can also do that for a free edge delamination. And this is more on micro scale again, where you have a fiber which is fractured and the shear lag layer which is related to it. We can then also introduce residual thermal stresses. And of course, yeah, maybe you have a hard time to believe this is possible. So we also are a bit necessary doubt. And we first want to validate this. So we built a lot of finite element models, which are only meant for verification and validation of our models. And here you see all the typical loading conditions in classical laminate plate theory. Also here you see the bending moments and twisting moments that are applied. And you even see a very detailed RV with ply cracks, delaminations from the ply cracks. And then we apply not only in-plane loading, but we can also apply curvature, so second order periodic boundary conditions, and then look at the local stresses and the homogenized behavior. and compare it with the solutions we get from here. And this we have done over the years very extensively, so these models are fully validated. And this has a runtime of a few hours already. Look at a very fine mesh, and it's a 3D problem. And the runtime of the variational models is 1 second, sometimes even less. Why do we need these short runtimes? Because there is still one thing missing. How will one scenario evolve to the other one? So here I have an example. I have 3 ply cracks. Suppose this is my current condition. What will happen next? Is the next scenario another ply crack here in the middle? Is it maybe delamination from the ply crack tips? Is it maybe fiber failure, which is happening here? Or maybe it's all 3 of them together. And how do we decide on that with an energy-based approach? So we will calculate all these scenarios and keep the one which is energetically most favorable. And that is why the calculation time must be so short, because we have to assess the different scenarios and keep the physically most relevant one. If we apply this now, here you see a validation experiment. The experiment is from Stephen Hollett's group on a quite specific laminate. And here you see our simulation. So we report stress versus strain. And you have here the stress versus displacement in the experiment. I don't have the time to lead you through every single detail, so you have to believe me that the sequence of damages that we see here in our simulation corresponds very well with the observed sequence in Stephen Hollett's experiment. But you also see that here you have these drops, and we don't have them here. So that is because strain and displacement are obviously not the same. So to combine this damage-based and physics-based modeling with validation experiments, you also need a lot from the experiment. You need good observations of ply cracking, delaminations, and to do that online is really not easy. So this brings me back to my last section, like with the micro scale, the experimental challenges. How can we get more from one experiment to support these modeling efforts? Here you see a picture of a typical experiment in our lab. So here you have the sample, which is clamped. And here you see the infrared camera. Remember the temperature measurements I showed you before. And here you see 2 cameras, which are measuring in a contactless way, an optical way, the strain on the surface. This is with digital image correlation. For those who would not know it, you apply a speckle pattern on the surface. You follow it with the 2 cameras. And from that, by correlating successive images, you get the strain in a contactless way mapped on the surface. You also see some illumination and some other things. But what did we try in the past few years? This is looking at the front surface with 2 cameras. So if you first look to the left to the schematic figure here, we already have the speckle pattern on the front surface where we look at with 2 cameras. And now we add a speckle pattern at the edge. And we also look with 2 cameras to it. And we have an extensometer, which is just a validation for the strain measurement in actual direction. We always do that as just a backup. These are all synchronized. All these measurements are synchronized with force, displacement, thermocouples, and so on. And here you see what we see with the cameras. So this is the frontal DIC pattern, which is basically the green arrows here, which you do not see here from the edge. And these are the edge patterns that the 2 cameras from the side see. And what can we get out of these measurements? First of all, I will show you the front DIC. This is still, let's say, more standard. And I will show it to you in fatigue. The reason why I show it in fatigue and not in a static loading is to show you also a bit the power of this method, because in fatigue you can really extract a lot of data from this. So here you have 2 experiments, experiment 1 and 2, where for both of them I show you the longitudinal or axial strain, and the transverse strain. Be careful, this is logarithmic scale, so this is the running in of the machine that you see. And then when the machine ramps to the final amplitude, the fatigue test continues and you see a slight increase in the longitudinal strain. On the right, you see basically more or less the same information, but combined with the load cell data. So here we have the stress strain hysteresis loops. On this side for the axial strain, and on this side for the transversal strain. Again, logarithmic scale, and blue is the first cycle, red is the last cycle before failure. And you see that the hysteresis loops shift from left to right, and here from right to left for transverse strain. So you can get, we have many data points for an individual cycle, so you can really measure the energy loss in one cycle and also look at permanent deformation over time. That was the frontal DIC. If you now go to the edge DIC, we can do even more extraction of data. So here you see the images here from the edge taken, and we show here the actual displacement. And you see there are a lot of jumps or discontinuities, and every one of these discontinuities is a crack. Because when you have a crack, which is then oriented like this in the 90-degree ply, that means that the displacement field is not continuous across the crack faces, and you get a jump there. So if we now have here a line drawn and we plot it in a graph, it looks like this. So this is the actual displacement versus actual position. And every tiny jump here is a crack. So all the green lines are detected cracks. This is very nice because if you now let your fatigue test run for a week and your system is there, you can measure day and night and get a crack density versus the number of cycles. So you see for different layups, you see the crack density growing over time. And also, like we know for fatigue, then at some point saturating to a certain value. You can also, because you have the stress strain curve in the actual direction as well, you can also show the stiffness degradation versus the crack density. And then we are there because this is physics-based, a relation between the damage at micro scale and the stiffness, which is a structural macroscopic property. And we can do even more. Here you see, again, our variational model can say the relation between the crack density and the stiffnesses, all the stiffnesses. So you see if you have in a 90-degree ply some cracks, that some stiffnesses just stay the same, but other stiffnesses, especially the transverse stiffness, the shear and transverse shear, they drop a lot. So the nice thing here is, and we use that a lot, that you do not even need to know a damage model in fatigue to have the evolution of damage. You can also just freeze the damage state at a given moment in time, count the number of cracks. I have a certain crack density, I have a certain stiffness reduction for that crack density, and then check with your variational model if that crack density and that stiffness reduction match. And if the stiffness reduction is higher than the one that you get from your variational model, it means there are other damage mechanisms playing a role, like delamination, like fiber failure, which contribute additionally to the stiffness degradation. And finally, again, validation. Do we trust this? So after a fatigue test, we do not run till final failure, so we stop before. And then under the microscope, Joseph in this case is the victim who manually measures all the cracks and compares the crack density with a measured one from the digital image correlation. And this way we get another verification, yes, this works. And now we are even trying to get nanospeckle applications. So in the background, you see the individual glass fibers and the speckle pattern is on top to get even higher resolution in measurements. And then I promised the last 5 minutes, unidirectional is still simple, Well, I just want to give you a peek view on, I can tell the same story for textile composites where we are also working on, but I will just limit it to short fiber. So there the geometries are much more complex. Typically you use injection molding in automotive and you get quite complex parts with sharp corners, a lot of variations in wall thickness and geometry. So there, typically mean field homogenization approaches are used, like for example, in commercial code Digimat. What we can already recycle, let's say, is our polymer models. All the nonlinearities of the polymer that we had for the micro scale of the unidirectional composite, we can still use. But we get other complexities on top of that, and that's what I want to show you in the last minutes. First of all, 0 degree is never 0 degree. What do I mean with that? If you inject a dog bone sample with short fiber, so directly into a mold with a dog bone shape, or you make a plate injection molded and then you cut your samples. And then you can even choose where you cut your samples, close to the injection gate or further away, or if you take longer samples or shorter samples. But here you see mold flow simulations from Leerteker, where we work together in a European project. And there you can see that fiber orientation is never 0. And indeed, I can prove you in more detail. Here you see a cross-section through the thickness. So this is the central part of the geometry, and here is the top. So we only see about half of it here. And then you see you have a quite aligned part on the top. And in the middle, the fibers are mostly under 90 degrees. So this has to do with the flow of the polymer and also the shear stress gradient in the flow. So this is called a core shell effect. And also even the volume fractions are not the same. So this already complicates a lot what we have shown in unidirectional arrangement. How do we try to approach this? Again, with the same philosophy as what I showed before. We start with a representative volume element with short fibers, but here they do have a 0 degree orientation perfectly. So all the fibers are under 0 degree. And then we try to calibrate with these models an anisotropic plasticity law, which is a homogenized behavior. And then only we start to add the orientation effects and then go to the core shell effect, where the orientation in the middle is different than from the shells. And then we can treat it as a homogenized material. So here you see that this can work. This is the stress strain curve. The circles are the finite element simulation of this RV. And then the fitted, because in this case it's still a fitted line, is the anisotropic plasticity model. And that we then use with different orientations and built in the orientation tensor from these sides. And then to conclude my story, you see always my logic with the simulations and then the experimental challenges. Just a few last ones to close the story. Experimental challenges, and I also want to show you one very down to earth. You want to have this sample here, 1 millimeter, 3 millimeter high, to look at these fiber orientations. And I showed you here the fibers are more or less 90 in the middle, and here they are more or less aligned. And we would like to segment the individual fibers. That means that in a micro CT scan, you really need a very low voxel size. But that means that you also need a very small sample. Now, if you don't want to lose your hands or your thumbs in the diamond saw, then even cutting these samples is already a nightmare on itself, because this is, in this case, it was thermoplastic. So also the heating that you introduce by cutting should be minimized. But now we managed to make very small samples here. Yeah, for those who are in Europe, you will recognize the 20 euro cent coin. For the others, you have to believe me that this is about 1 millimeter size. And this is a small coin in euros. And then we can do a CT scan, and indeed, by deep learning algorithms, we can segment the individual fibers and get some statistics on the fibers. And a second experimental challenge is definitely interfacial characteristics. So Marino Karazmin's group showed already in the past with SEM images that in the interface, there is also happening a lot in short fiber. And there we try to isolate this phenomenon and have it in real time observed. So here you see some measurements where we have a single short fiber. So this is about 7 microns. And we can observe in transverse loading, because most interfacial tests are in shear, but this is in transverse loading. We can over time see the progressive debonding of a single fiber. And this way try to understand how these debonding mechanisms work. I'm at the end of my presentation, so in conclusion, I will not, sake of time, repeat all of them. I think, and I hope I brought through the message, which is for me a very important one in my own belief in modeling composites, that numerical and experimental integrated approach is really key. And of course, many things were still not highlighted here in this short webinar. But I invite you, we recently edited a book with many colleagues in the field on continuum mechanics modeling, which is from end of 2000, so it's still very relevant as a book. And here is my email address if you would have any questions. I will not serve as your personal hotline for problems in composites, but feel free if you still have any questions after this 1 hour, I'm happy to answer. With this, I can acknowledge the support of all people in our group of funding organizations and industrial and academic partners we work with. And I'm very happy to listen to your questions. Thank you very much.
Thank you very much, Professor vanpaepegem. I'm Jonathan Goodsall. I'll be asking questions, and so a reminder to the audience to please upload questions into the Q&A box, and those that we don't address here in the time we have, we will send to our presenter, and he can choose to respond to those individually at his leisure. But a couple of questions here, if I can begin. There's a number of questions that stimulated by both the micro and macro approaches which center around how you can continue to bridge between those scales, and maybe a comment from you on where you see this going. Of course, people always asking questions about how do you get the micro closer to the macro and vice versa. With the increase of computational power and these tools, where do you see things going in, say, the next 5 or 10 years with this ability to do these multi-scale modeling challenges?
Yes, thank you. I maybe say a bit, like how we look at this for the moment. We think from structural scale down to ply scale, we are already quite close to really physics-based modeling. So as you could see, I will try to quickly find, I'm almost there. So we are already integrating quite some damage mechanisms in a correct way, and the delaminations is very recent. This was really a challenge to include those. So up till the ply scale, we are quite, maybe I can also show you something else, because this is very important related to your question. For example, even if you stay at ply scale, this is for us also an important check. Can you model with your damage model these 3 layups? So you see from classical laminate plate theory, they are identical. But once there is damage, they are far from identical. Here the 90-degree ply is constrained. Here it's at the surface, and here it's much thicker. So the damage will be different. The free edge delaminations have even different signs. So this is a very powerful validation, which continuum damage mechanics models can often not take into account. So that's first part of the answer. About the micro scale, there honestly, we see it more as getting insight into the behavior of a composite rather than trying immediately to calibrate ply-based models. The reason is that I showed you some insights into like the self-heating problem. We are currently also working on, because the self-heating was still at ambient temperature. The temperature was not changing. It was just the internal temperature which changed. But we are also working on projects, especially for automotive, where thermomechanical behavior is important, where also the ambient temperature is changing and crossing the glass transition temperature, and you get a lot of nonlinearities. And they're trying to really have a yeah, an exact prediction from the micro scale up, we still struggle mostly with the interface. So the interface properties and what happens around are very, very close to the interface is difficult, especially if you move away from the carbon epoxy composite, which is okay, well studied, but once you move away from carbon epoxy, for example, to get interface data on glass polyamide 6 or carbon polypropylene or other combinations that are now emerging, you hardly find any data. So that is still a big challenge, and that's why I showed you in the last slide, we try to also isolate this interface to try to measure it. But I would say for the coming years, we use the micro scale more for insights in how all these materials work together and how, for example, the self-heating has to be calibrated in a correct way to have a decent material model for your polymer. And for structural behavior, rather try to come down to ply scale, but that is a bit the level where we are for the moment. I hope this more or less answers your question.
Thank you very much. A follow-on question with that. You've brought together both experimental and simulation approaches with some comments on experimental challenges. If you had your wish, what experimental technique or what measurement would most affect the simulations? If you could have one or two things experimentally nailed down that today are very challenging to do.
Yeah, it's again a bit related to the interface. So I will go back to this slide here. So this is now a single fiber in a polymer, and we can have well-controlled testing conditions. But for example, if you want to now follow how these damage mechanisms evolve over time, this is also post-mortem after failure. There are some experiments in synchrotron, so where people go to synchrotron here in Europe. You have the one in Grenoble, in Zurich. You have in Japan. You also have a few. I guess certainly you have in the US as well. So you need to write a proposal. It takes a long time, and then you get a few hours beam time on a synchrotron, and there you could start to see these things in situ. But what I would really hope for, but I think it's technically really very hard, is to get such things more to the lab environment, that you could follow damage mechanisms over time, but in real time, not post-mortem, not because also our mechanisms that I showed you for the ply cracking, they are observed from the edge of the sample, not in the volume. You can argue, yeah, with glass fiber, you can of course see through it, but we deliberately don't do this because for carbon, you're already stuck because it's not transparent. So we try to develop it that it works for all composites. So we observe from the edge. If we could observe in a lab environment in situ how damage mechanisms evolve in the bulk of the material, this would be great. But I've seen it already for synchrotron measurements, but besides that, it's really hard. So that would be a nice wish, but I don't know which invoice is related to it.
Thank you. Let me ask another question that came up as you were looking at the 090, 90, with talking about the free edge stresses.
Yeah.
Today, what's the state of the art as far as being able to model the effect of free edge stresses? What can be done analytically and computationally today?
Yeah, so that's something we could solve with the variational methods. So the free edge delamination, you probably know, not even delamination, but just the stresses elastically. If you want to do this in finite elements, you need an extremely fine mesh. And basically in the end, it's a kind of singularity. So you have a problem and it runs for a very long time. So with variational models, we can have the free edge stresses calculated. Honestly, to what extent industry is already including this, I have rather the impression that as an academic, we have then the role to, for example, compare different layups. And of course, now I only show two orientations, but if you have a complex layup with tens of layers, we can in an analytical way very fast give recommendation which order, which sequence of these different angles gives lower or higher interlaminar stresses, just elastically. And I guess for industry, this is about as far as we can go for the moment, because really integrating interlaminar stresses like around every bolted or riveted hole in a default analysis, I think it's not so easy, at least in certain industries, this is not common. But to give recommendations more on the design level, let's say, this is certainly possible.
Thank you. And thank you for the overall presentation and for the questions and answers. We've come to the top of our hour. Professor vanpaepegem, we thank you, and we thank the audience. We appreciate everyone's participation both today and throughout this second series of the webinars. This concludes the webinar today and also concludes our series until the fall. We'll be looking for emails from us and also be checking cdmhub.org, where we'll post information about the webinar series as we resume again in the fall. So again, many thanks to our presenter and to all the participants. And we wish all a good summer and look forward to convening again in the fall. Thank you.
Thank you very much.